Have you ever wondered if you could take a bunch of, let's say, B squad players and somehow turn them into a championship-winning team? Well, in the world of machine learning, that's exactly what boosting does. It's this incredible technique that combines simple, weak models to create one super powerful predictor. So let's dive in and see how it works.
It sounds a little counterintuitive, doesn't it? But the answer is a resounding yes. This is the whole idea behind something called ensemble learning. It's basically applying the wisdom of the crowd concept, but instead of people, we're using algorithms to build a supermodel from a team of simpler ones. So here's our game plan. We'll start with the whole strength in numbers idea. Then we'll compare boosting with another method called bagging. We'll meet the key algorithms in the boosting family, see exactly how they learn from their mistakes, and then put it all together with a real-world example. Right, so think about it like you're putting together a team of specialists. Instead of relying on one single genius to solve a really complex problem, ensemble learning brings together a bunch of simpler models. Each one has its own little perspective, and when you combine them, they produce a final prediction that is way more accurate and reliable. Now, the building blocks for this whole thing are what we call weak learners. And honestly, the name is a little unfair. A weak learner is just a really simple model, like a decision tree that only asks a single question. We call that a stump. By itself, yeah, it's not going to win any awards, but its simplicity means it's super fast and focused, which makes it the perfect team player in a bigger, much smarter system. Okay, so you've got this team of models. How do you actually manage them? Well, there are two main playbooks, boosting and bagging. Both are trying to get to a stronger final result, but they go about it in completely different ways. One is all about collaboration, and the other is about independence. And this table really lays out the difference. See, bagging is like a group project, where everyone works on their own piece at the same time, totally independent. Then you just average the results. Boosting, on the other hand, is more like an assembly line. Each model learns one after the other, and its main job is to fix the mistakes of the model that came before it. This means bagging is great for reducing what's called variance, basically making the model less sensitive to the specific data it was trained on. Boosting, however, is a master at reducing bias, those core errors in the model's basic assumptions. So if you're going to remember one thing, make it this. Bagging gets its power from averaging out errors across independent models. Boosting gets its power by building a sequential chain where each model actively learns from the mistakes of the last one. This idea of sequential learning was so powerful that it didn't just stop with one algorithm. It kicked off a whole evolution, creating a family of algorithms that have just gotten smarter and more powerful over time. The story really starts in 1997 with AdaBoost. It was the pioneer, the one that figured out how to force new models to focus on the toughest examples by changing data weights. Then came gradient boosting with a huge breakthrough. It asked, instead of messing with the data, why don't we just build new models to predict the errors of the old ones? And that brilliant idea led us to today's champion, XGBoost, which took that concept and just engineered it for pure speed and performance. And that steroids metaphor, it is absolutely perfect. The genius of XGBoost isn't really a brand new idea, it's in the engineering. It's optimized for things like parallel processing, which means it can chew through massive datasets at incredible speeds. That's why it's the go-to algorithm for everything from data science competitions to demanding real-world applications. All right, we keep saying these models learn from mistakes, but what does that actually look like? Let's pop the hood and get into the mechanics of our two main players, AdaBoost and gradient boosting. AdaBoost, which stands for adaptive boosting, has a really cool and intuitive process. It starts off treating every single data point as equally important. After the first model gives it a shot, AdaBoost looks at what it got wrong. Then, it increases the weight of those misclassified points. This literally forces the next model in line to pay extra attention to the tricky examples the first one missed. You just repeat this cycle, and in the end, you have a whole team of specialists that contribute to a final, weighted decision. Gradient boosting takes a more direct route. It makes an initial prediction, and then it calculates the errors, the difference between its guess and the actual truth. We call those errors residuals. And here's the genius move. The next model isn't trained to predict the original target, it's trained to predict those residuals. By adding this error prediction back to the original guess, we slowly but surely fix our mistakes, with each new model getting us one step closer to a perfect prediction. Okay, theory is great, but let's make this real. How would you actually use these algorithms to solve a super important business problem, like predicting which customers are likely to default on a loan? So the goal is simple. Figure out who's going to default. We're going to throw all three of our boosting algorithms at the problem. Now, the biggest trap you can fall into here is something called overfitting. That's where your model basically just memorizes the training data instead of learning the actual patterns. So to see how well we're doing, we're going to focus on a metric that's critical for a bank: recall. In plain English, that just means, of all the people who actually defaulted, how many did our model correctly flag? And no big surprise, the first run was a textbook case of overfitting. The models looked like geniuses on the training data they'd already seen, but as soon as we showed them new, unseen test data, their performance just tanked. They weren't learning, they were just memorizing. So what's the fix? Well, it's a process called hyper-tuning. You can think of it like tuning a high-performance engine. We go in and carefully tweak the model's settings, things like how many learners are on the team or the learning rate that controls how much influence each one has. The whole goal is to find that perfect sweet spot where the model is powerful enough to find the real signal in the data, but not so powerful that it gets distracted by all the noise. And after all that tuning, wow, the results are pretty dramatic. AdaBoost and gradient boosting definitely got better, catching around half of the actual defaulters. But look at XGBoost. Its performance just skyrockets, hitting a recall of 0.90. That is a massive leap, and it shows you exactly why XGBoost is king in so many situations. So, what does a recall of zero point 0.9 actually mean for the bank? It means they can now correctly identify 9 out of every 10 customers who are actually on a path to default. When you're talking about managing financial risk, that kind of predictive power is an absolute game changer. But, and this is a really important but, there's no such thing as a free lunch. To catch that many defaulters, the model had to cast a much wider net. And that means while it correctly flagged more at-risk customers, it also incorrectly flagged more safe customers as potential defaulters. This is that classic trade-off between recall and precision, and it's a constant balancing act for anyone working with this stuff. Which really brings us to the final crucial question. Boosting algorithms give us unbelievable predictive power, but with that power comes a huge risk of overfitting, of learning the wrong lessons. So the real art and the real science of using these tools is mastering that delicate balance, tuning them just right so that we capture the true signal from our data without just memorizing all of its noise.